Issam Ishaq to present the briefing of his work named Smart E-Waste Management System Utilizing IoT and DL Approaches. You have 15 minutes. Thank you.
Excuse me, please, if you help him, if you Daniel.
My name is Daniel Foskerician. I'm a PhD student in a joint program by Al-Quds University, Arab American University, and Polytechnic University in Information Technology Engineering. First of all, I'm going to present you a research article entitled Smart E-Waste Management System Utilizing IoT and DL Approaches, supervised by my doctor, Issam Ishaq. As a brief introduction, electronic waste, or referred to e-waste, is considered the fastest growing waste stream globally. As a consequence, it was entitled by the United Nations as Tsunami of the E-waste. E-waste nowadays represents a major global concern, especially in developing countries like my country, Palestine, since it contains hazardous substances, and if not managed properly, it can lead to a harmful effect on human health and environment. Thus, there is an urgent need for smarter, safer, greener systems to handle such e-waste more efficiently. If we look into the literature, we will find that the majority of studies concentrates on general waste management. In specific, it tries to design smart dustbins or bins focusing on recycling or IoT-based segregation. However, minority of studies focuses on e-waste management, and in this domain there are two separate directions, one for object detection and one for monitoring. In this study, we presented the design and the development of a smart e-waste management system utilizing two main concepts: the Internet of Things, IoT, and TensorFlow-based deep learning models to support the Green City initiatives and to meet the sustainability goals. The proposed system actually provides two main operations. One is for object detection, utilizing TensorFlow-like framework with a pre-trained object detection model. And the second operation is providing continuous monitoring of the condition of the bin in terms, for example, temperature and humidity to prevent any undesirable events such as fires. In addition, it provides up-to-date information to different stakeholders regarding the e-waste count, filling level, or the volume of the e-waste. Regarding the object detection model, we have followed 6 main steps to develop the object detection. First, choosing the computing paradigm, whether we are going to implement the whole processing on cloud, on fog, or on device. In our project, we have decided to put the whole processing on device for two main reasons. First, the Raspberry Pi camera, which captures images. The file size has 15 megabytes, and transmitting it through the GSM as a communication transmission medium will yield higher latency and will increase the response time. Second thing, with the availability of frameworks such as TensorFlow Lite, we can optimize any model to work on devices with limited capabilities. Regarding the deep learning framework, as I told you, we are going to use TensorFlow Lite framework, which is an open source cross-platform deep learning framework that can convert any TensorFlow model into a special efficient format called buffer, TF-Lite buffer, and optimized for speed and storage. Regarding the model and the architecture, we have decided to choose Efficient Depth Lite, which is a mobile IoT object detection model. The good thing about this family is that it consists of 5 main models from Lite 0 to Lite 4. As we can see here in the table, as we go down through the table, we will get more accurate models. The mean average precision increases, as well as we will have a higher latency as we go down through this family. If we make a simple comparison between Lite 0 or Lite 4, we can see that Lite 4 is more accurate, definitely. These two figures represents a comparison between the size and the latency versus average mean precision. As we can see here, if you want to get more accurate model, the size of the model will increase. In addition, the inference time will also increase. In this project, we have used the Lite 4 model since it has the highest mean average precision, although it has also the higher inference time, which is 2 seconds, but I think this is an acceptable state for our project. Okay, in order to train the model, we need to extract images. We have collected 1,000 images from Open Image Dataset version 7, which consists of 9 million images annotated for object detection. In our project, we have collected for 5 main electronic objects such as smartphones, headphones, monitors, mouses, and keyboard. We have divided the dataset into 80% training, 10% testing, and 10% validation. Okay, to train the model, we have used the TensorFlow Lite model maker library, which uses the concept of transfer learning. Transfer learning means that we have a model that is already trained, and we use it as a starting point to create a custom model. The good thing about transfer learning is that we reduce the learning time. In addition, we don't need a data set that is huge in terms of the number of images. As we can see here, the pipeline of the training, at the end we performed quantization and we converted our model into a TensorFlow Lite model, and we get a mean average precision of 76.9%, which is a good number for the moment. Regarding the system structure or architecture, the detection will be performed through the Raspberry Pi 4. The monitoring and communication will be performed through the electron particle with 3G connectivity, which will be connected to several sensors. Okay, and the communication will be done through the GSM communication medium, and we will store the data set or the data in the ThinkSpeak cloud platform. Okay, I don't want to take too much time, but regarding the system workflow, the bin will start by checking itself if it is under maintenance or if it is full. If that was the case, it will communicate with other bins in the neighborhood and try to collect different information, such as their location, their working status, their filling level, and will propose to the user the bin that satisfies the shortest path with the available capacity, and will display it on the display screen. if the bin is working perfectly, it will accept e-waste in its compartment, and once the user presses the run button and put the e-waste, it will capture an image using a Raspberry Pi camera and will transfer it to the TensorFlow-like object detection model. If e-waste is detected, then we will open the bin cap and we will throw the e-waste. We have used the infrared sensors to count the number of e-waste being thrown in the cab. At the end, we have used the ultrasonic sensor to measure the filling level. If the filling level exceeds a predefined threshold, for example 80%, we will notify the authorities to come and collect the e-waste. If not, we will read the load sensor and we will send the whole measured information to the ThinkSpeak cloud server. This workflow actually represents the fire prevention and detection. In the bin, we have used flame sensor and temperature and humidity sensor. But here, the main difference is that we will not send the data in a continuous way. We will measure the current reading versus the last reading, and if it exceeds a predefined value, we then will send it to the ThinkSpeak cloud platform to mimic the energy efficient process. I don't want to talk too much, but here we have created a system prototype as a proof of concept. Schematic diagram, the object detection model light 4, the response to the e-waste object detection, the monitoring e-waste bin condition, and here some graphs from ThinkSpeak web platform. Finally, regarding the system price, like it takes $270 approximately, which is justifiable in a way, because we will have a huge reduction in the amount of labor work in the traditional waste management system. Okay, as a conclusion, we have proposed a comprehensive smart e-waste management system integrating various sensors to monitor the current condition of the bin. In addition, e-waste object detection model was proposed to perform real-time waste detection and classification. We aim to improve the e-waste detection model in the future by adding other classes, increase the number of e-waste images per class, increase the training time so that we can improve the accuracy and enhance the flexibility of the model in identifying e-waste. Moreover, we aim to build an interactive mobile application that will be used by the end users to find the nearest e-waste bin from the current GPS location of the user. And thank you for listening.
Thank you, Mr. Daniel, for your presentation and for your work is very interesting. Now I will invite the audience if they have any question. Mr. Asad.
Thank you. My question is about sensors. Why did you use 3 sensors, 3 temperature sensors indeed? Infrared sensor,
Yes.
temperature sensor, DH level, and flame sensor. Is all sensors
Each one, oh my goodness. Each one will have a separate function. If you can see here in this figure. Okay, the infrared sensor will count the e-waste objects thrown in the bin. Regarding the humidity and temperature sensor, will be used to detect any undesirable events, such as if there will be a fire in this bin, and the flame sensor will detect any flames. Yeah.
These all sensors use are the temperature sensors. That's my question. In your system, you will use the infrared sensor for what? Infrared.
Infrared for counting the number of bins
the number of e-waste thrown within the bin.
Okay. Thank you.
You're welcome.
Thank you, and thank you, Mr. Daniel. We invite Mrs. Ibtihaj to continue the animation. We will.
But I want to thank Doctor for his invitation. Thank you so much. Thank you so much.